A 30.0 meter long extension cord is made from two number 19 gauge copper wires. One wire carries current to an appliance while the other wire carries current from it. What is the resistance of each wire at 20.0 degrees Celsius? The diameter of number 19 gauge copper wire is 0.912 millimeters, and its resistivity at 20.0 degrees Celsius is 1.67 times 10 to the minus 8 ohm meters. If the copper wire is to be replaced by an aluminum wire of the same length, what is the minimum diameter so that the new wire has a resistance no greater than the old? The resistivity of aluminum at 20 degrees Celsius is 2.65 times 10 to the minus 8 ohm meters. Let's begin this problem with a sketch. So this says we have an extension cord that is attached to an appliance. So maybe this appliance is a lamp. And this extension cord connects to a wall outlet. This says that one of these wires carries current to our appliance, while the other wire carries current away from our appliance. We're given that the extension cord is 30 meters in length, so each of these wires is 30.0 meters long. We're also told that the resistivity of this wire, and this wire is made out of copper, so I'll indicate this with the subscript C. The resistivity at 20.0 degrees Celsius is 1.67 times 10 to the minus 8th ohm meter. We're also told that the temperature is at 20.0 degrees Celsius. We need to find the resistance in each of these wires. Well, first off, each wire is made out of copper, and each wire is of the same length. So if we find the resistance for one wire, then we found the resistance for both wires. Now let's use the relationship that we found for the resistance of a conductor. Resistance is equal to the resistivity times the length through which the current moves divided by the cross-sectional area through which the current moves. Since this is a copper wire, I'll just say the resistivity of copper with a subscript C is equal to the resistivity of copper times the length of the copper wire, which I'll indicate with a subscript C, times the cross-sectional area of the copper wire. Well, we are given the diameter of each of these copper wires. So the diameter of a copper wire in our extension cord is equal to 0.912 millimeters. The resistivity at some temperature is equal to the resistivity of our reference temperature, which is typically taken to be 20 degrees Celsius, times 1 plus the temperature coefficient of resistivity times the temperature at which you're measuring the resistivity at minus the reference temperature. Now, in this problem, the reference temperature is the temperature at which we're measuring the resistivity at. So what this means is that the resistivity of our copper wire at 20 degrees is given, and it's given as the 1.67 times 10 to the minus 8 ohm meters. So with that said, we have enough information to complete this problem. We have the resistance of copper wire is equal to its resistivity times its length, both of which are given, divided by the area. Well, the cross-sectional area through which the current moves is given by the area of a circle. The area of the circle is given as pi times the diameter of that wire over 2 squared, because remember, the radius of our wire is equal to 1/2 of the diameter. This ends up being pi times the diameter of our wire squared divided by 4, which means that the resistance is the product of the resistivity and the length divided by pi diameter of our wire squared over 4, and this is simply 4 times the resistivity of our wire times the length of the wire over pi times the diameter of our wire squared. We're now ready to plug in numbers. We have that the resistance is equal to 4 times the resistivity of 1.67 times 10 to the minus 8 ohm meters times the length of the copper wire, which is 30.0 meters, divided by pi times the diameter squared, which is 0.912 millimeters, quantity squared. Well, let's cancel some units here. I see a meter squared in the numerator cancels with a meter squared in the denominator, leaving our units to be the ohm. So the units check, we can write then which means that we could write that the resistance of our copper wire, after plugging into my calculator, I get 0.767 ohms. Part B says, what if our wires are replaced with aluminum wires? What would the minimum diameter for the aluminum wire need to be for it to have a resistance no greater than the old wire? Well, the resistivity of aluminum, which at 20 degrees Celsius, is equal to 2.65 times 10 to the minus 8th ohm meters. And we want to know how thick this aluminum wire needs to be in order for it to have a resistance no greater than the resistance of the copper wire. So in other words, we could use this relationship. The resistance of the copper wire must be equal to. So in other words, we could use this relationship. The resistance of the aluminum wire must be equal to the resistance of the copper wire. Well, the resistance of the aluminum wire is given as the resistivity of aluminum times the length of the aluminum wire divided by the cross-sectional area of the aluminum wire. And that has to be equal to the resistivity of the copper wire times the length of the copper wire divided by the cross-sectional area of the copper wire. Now we should recognize that the aluminum is just replacing the copper wire. So the length of the aluminum wire is equal to the length of the copper wire, which means those lengths cancel on each side of this equation. We should also recognize that the area of the aluminum wire is going to be equal to pi times the diameter of the aluminum wire over 2, quantity squared. So we are actually looking for the diameter of that aluminum wire. And don't forget, the area of the copper wire was just equal to pi times the diameter of the copper wire over 2, quantity squared. This means that our relationship between the resistance of the aluminum and the copper is equal to the resistivity of the aluminum over the area of the aluminum wire, which is pi times the diameter of the aluminum wire over 2 squared, is equal to the resistivity of the copper wire over pi times the diameter of the copper wire over 2 squared. So notice we have a pi on each side of the equality. We have a 1 over 2 squared on each side of the equality. This expression then becomes the resistivity of the aluminum over the diameter of the aluminum wire squared is equal to the resistivity of the copper wire over the diameter of the copper wire squared. Rearranging and doing a little bit of algebra, we get that the diameter of the aluminum wire is equal to the diameter of the copper wire times the ratio of the resistivity of the aluminum wire over the resistivity of the copper wire. And that is underneath the square root. Well, let's plug in values for this. The diameter of the copper wire was given as 0.912 millimeters. And this is times the square root of the ratio of the resistivity of the aluminum wire, which is 2.65 times 10 to the minus 8 ohm meters, over the resistivity of the copper wire, which is 1.67 times 10 to the minus 8 ohm meters. The ohm meters cancel, leaving us with units of the meter, which is what we're going for. So since the units check, and we could do some more simplification here, the 10 to the minus 8 in the numerator cancels with the 10 to the minus 8 in the denominator. When I plug this into my calculator, I get that the diameter of the aluminum wire is equal to 1.15 millimeters. Now let's see if that makes sense. This is saying that the aluminum wire has to be thicker than the copper wire in order for it to have the same amount of resistance. Now that makes total sense because remember, resistance is inversely proportional to the diameter squared and directly proportional to the resistivity. Since the resistivity of aluminum is higher than the resistivity of copper, it makes sense that we're going to need a thicker wire in order for the overall resistance to be the same. That thicker wire is compensating for the fact that the resistivity of aluminum is higher than that of copper. So this answer makes sense.